good time to do a talk about cloud, just to have this great title of the talk, the EERIE Santa Cloud. Nikolai, is this actually recorded, the session, or?
Yeah, the session is recorded, so it's done automatically. Okay. So I see that it's recording now in progress.
Okay, I think we need to thank Javi for creating this nice picture here of the Santa Cloud. However, it's unclear to me how the Santa Cloud got access to Levante, but yeah, it somehow did. EERIE is funded, as you know, from the EU, the UKRI, and the Swiss State Secretariat for Education, and we thank them a lot for supporting us. So the topic today is cloud, and I want to give you an introduction into what is cloud storage and how we can make use of institutional cloud storages. For that, I give you a kind of introduction of FSPEC and ZAR, and also discuss how to host existing climate data in the cloud. And at the end of the talk, if you have time, I hope you have time, you must have time, I am going to show you updates on the EERIE data workflow. So in my last talk here in the EERIE Science Hour, which is not so long ago, I showed you this picture here of the 3 different types of storages that we have at DKRZ Levante. You have cloud storage, you have the file system, which is the most usual storage type where you work on, so which you are familiar with to work on. It's a high performance storage for computing jobs. And then we have the archive, which is low cost long-term storage. And today we want to talk about the cloud because we have the exceptional quota here for 100 terabytes shared EERIE data space for our project. Yeah, on file system at Levante, we are nearly full with 1 petabyte of EERIE data. So I think it's a good time to learn how to work with cloud. And yeah, I want to underline this with this, which you might have also thought already, oh no, we are running out of disk space again, but hey, what's this cloud storage? So the goal is you will be able to use cloud storage wisely if you behave well and listen. Yeah, what is cloud storage? A cloud is defined by 2 major things. So cloud storage is accessible via HTTP. The communication with the cloud storage goes via HTTP, of course, through an API. And the second thing is that the cloud is an object storage, and object storages don't have file systems. And those are the 2 major things which define a cloud storage. So, and because of this definition, there's a specific purpose of a cloud storage. And this is, we want to host the same kind of immutable data without a server on cloud storages. And this can be, per definition, images, videos, and music, but it actually can also be climate data if it fits into the cloud and is adapted to cloud and optimized for cloud storage access. This is mainly because of the missing file system. So the idea is that if you cannot organize your data in so much directories and you only have like a bubble storage, then the idea is that it would be really nice to have only one kind of data inside this, like images, videos. And, you have to use a good identifier to find this data, and the identification of the data is mainly done on user side. So cloud storage is no high performance storage. So if you work on the Lustre file system, you have the best latency. You have also actually the best throughput if you stay on the system, work with the system. But it is also fair to have some climate data in the cloud, and fair is here the acronym for findable, accessible, interoperable, and usable. And this comes of the features of the cloud. So the 2 basic ones that I already introduced means for the user the following advantages. So if you have access via HTTP, most software is actually able to understand it because it's the absolute standard protocol. So The next thing would be that the software also has to understand climate data, but we have some software tools like ZAR, which allows us to work with climate data via HTTP. But in general, that can mean enhanced interoperability. And if we have no file system, but a key value object storage, this results in less namespace conflicts. So if you have a script and you put in your local file path into the script and then you share the script, but the people who you share the script with do not work on the same file system, the scripts won't work. This cannot happen if you work with cloud storage data, because you have an URL to the data, and this is unique for the globe. Also, we can define access control list. So data access can be without any authentication. This is different to Lustre, of course, where you have to log in. So that can mean unrestricted and open and fair data for everyone. The cloud storage is independent from the computational cloud. So it's independent from Levante compute. So if Levante has a maintenance, it can be that you still have access to the cloud storage. That would mean that it can be resilient, but we don't have any backups for the cloud storage. That is something we have to consider. And we have some technical requirements from the cloud that the object size, so the data size, must be rather small. And this means that we actually force the data providers to provide us data with a highly granular chunk-based access. And here is the data workflow, how that should look like. So on the right-hand side, we have the cloud storage. On the left-hand side, the user with his or her laptop. And the user uses a Python script here with the OpenZAR and EERIE, and then loads data into the memory, but only the data that is actually needed from an array. And this array here has some chunks along the dimensions, and this is the lowest granularity that can be actually saved. It's just bytes for one specific chunk, and the access is only chunk based. And all this happens via HTTP. So important to say here, this should work from everywhere. So you can also work with the cloud storage without being on Levante. You need some access keys, and we are going to see that in the next slides. So how is DKRZ's specific Swift cloud storage organized if it has no file system? A cloud, and this is, so the general cloud has two different layers. The container hierarchy is the first level of this hierarchy, and it's the only thing that is kind of comparable to a directory. The container can be temporarily or permanently shared with an access control list. And inside a container, there are objects, and objects are just stores of bytes of data. You cannot have a specific individual access control list for an object. And all containers are saved in one account, which is the absolute top level here. And this is specific to Swift, I think. However, it's probably only named differently in Amazon S3 and Google Cloud Storage. So for our account, for the ERIE project at DKRZ, the BM1344 or BK1377, we have a quota of data that we can use and create container for. If you have already seen a Swift URL, so an URL to cloud storage, this hierarchy is actually translated to the URL. So you have always a kind of an account hash, which translates to our BM1344, and then you have a container name, and underneath there are objects. Objects can look like that they contain some directory, but actually they don't. So all this is actually one object, and you cannot access the directory with where the slash is. That's not a directory. We have different interfaces to work with the cloud at DKRZ, and we are going to look into all of them. So Swift browser DKRZ.de is actually the GUI, which is kind of handy and a good starting point. It asked us here on the login page to log in with an account, a user, and a password. So account can be both the project account, which would be BM1344, or if you join BK1377, you can use this. Then your username, in my case, it's K2042 and so on. You have your own username, and then you put in a password, and then you log in, and then you are in the account of the cloud storage. You can see already some containers. And this is me, and this is Julia, and you can create a container by adding, clicking here on plus, and then create in a container. And yeah, so I would say that it would be a good idea if you have specific user ID containers in our shared account here. So I can look into Julia's container actually and see what's in there, and you can look in all the other ones that you should be aware of. Yeah, going back to this. And then we have on the command line interface on Levante. If you're on Levante, you can use a module that is available on Levante, the Swift client. I would use a module avail and then grep for Swift, but I put here a command line. And but what we are going to look a bit more in detail now into it is the Swift spec. So a Python package which is named fspec, and it's really low level, but it's actually where the magic happens. And I think it's not so hard to understand what happens there. And for that, we have a new notebook, which I shared on the hackathon repo in the Nereos tutorial here. And maybe it's also a good idea to share the entire presentation with you, right? Maybe I should do that. And put it just in the chat. All right. Okay, I'm going to show you this notebook in my Jupyter because it's a bit larger here. So what is fspec? Fspec is actually a Python package which provides a unified Pythonic interface to different backend storages, file systems and byte storages. And it has two main concepts. And the first one is the nicest thing, I think. It's a file system class which provides uniform functions which you know from the Linux command line, like copy, remove, cat, make dir, and all these basic Linux commandos work then with this fspec tool for every kind of backend storages. For example, also the DKRZ cloud storage. And for that, we need plugins for the backend storage. SwiftSpec is a plugin for fspec, which is now installed in the unstable kernel on Levante. If you use in Jupyter Notebook, you can use unstable kernel. If you use a script, you can use environment as well. You can also work on your local computer with the cloud, as I told you. Then you have to install the SwiftSpec via pip. And in this notebook, we learn a bit about fspec. We have to prepare a bit the content of this notebook. For example, we have to create a container in the project space because this is not yet possible with the fspec SwiftSpec plugin. And then we have to create an access token and load this access token in a script. Access tokens are valid for 1 month. You can also create some session tokens with the API, but we are looking here too, and with this access token. For this, we use some bash commandos. We load the Python environment, and then we use the Swift token new commando to create actually a token, which is then saved in our home directory afterwards in the Swift env file. And if we write the two resulting variables into a mytoken.py file, then we can import this into the script. And this is kind of important because we don't want to have our token, which is also in this file, visible for others. So we have to hide it a bit. Two variables are in this file, namely the auth storage URL and the auth token. And if we put this in an environment, then the Swift spec can actually use this and has access then to the cloud storage. And here's an example how this works. So we initiate here or instantiate an Swift object, Python object with the fsspec file system command, use the Swift protocol. And then we can use basic Unix command like ls with this fsSwift object. For example, on the auth storage URL, which was in our Swift and one of these variables, one of the two. Then we can see, oh, we have the DKRZ scratch, the hackathon results, and a K204210 container in this account. Right now, I think the one from Julia is missing, but it would be saved, shown here as well. The auth storage URL is internally translated to a Swift URL. We can kind of skip that just to explain why Swift is here in the beginning of the URL. That actually is kind of handy for fsspec to understand that's already a Swift. That Swift has to be used for understanding this URL. So the Swift API calls needs to be used here for this URL. The US shows us the bit size of a specific container. In this case, the hackathon results have something like 26 megabyte. We can create a directory. However, this is only a virtual directory because it doesn't exist according to the hierarchy levels of a cloud. We can create objects and files. And with this typical Python commando here, we create a new test file into the cloud and write just some bytes into it. This looks kind of familiar to you if you work with Python, where you would actually use this without the fsSwift. You just would write with open, and the difference here now is that you use the fsSwift.open instead of open. We can also copy files. For this, we can use fsSwift.pipe, and then we pipe into a new file the content of the old file. And if we do that and we do an ls on that, then we see that we have new test file and new test file 2 in the cloud. We can remove all this with .remove, and we can also recursively remove that. And then we see there's nothing else anymore under this URL. The mapper, and this is kind of shift in thinking of how storage works. So what we can also do is we can create something like a Python dictionary for a specific directory or URL. What we're doing here is we use a Swift account URL and add prefix for our container, and then we use the get mapper function. And what we then get is actually a Python dictionary-like object. The cloud mapper has keys and values. And keys, as we see here, this is another mapper, but it's also a mapper, are just the file names or the object names underneath this initial path. So I skipped a bit. We are using here a disk mapper on some storage from Simulp 6. And use the keys from that. And you can see in this path, we have some files, not netcdf files, tasnetcdf files. And the mapper actually stores all the objects or files inside this Python dictionary. And if we have a cloud mapper and a disk mapper, then we can copy and sync these mappers by just using the update function as if it would be a Python dictionary. In this case, we update the cloud mapper with the disk mapper, and that means we copy all the files or the objects from the disk mapper into the cloud. And if we do so, we see that we have in the fsSwift, under the cloud mapper, which also stores the URL under .root, All these netcdf files were transferred to the cloud. So this is kind of an easy way to sync or copy files from, and across file system also. So we can use different types of backends here for the mapper, as long as FSPEC understands it. And then what's the application here of FSPEC? We can use all these URLs with FSPEC to just directly pass it to XArray. We now transferred it to the cloud, and if we open these URLs with FSPEC open, and then we have to do another open because we are not using this with statement anymore, and we save that in a list, then we can pass this list to OpenMF dataset, and we use now the cloud as the backend and open the data from the cloud, and we will see after a while that we get this DS dataset view. We can also save data with XArray to the cloud with the mapper, or with the URL. We use the root of the mapper, which is an URL, and we add our new virtual directory, in this case test_zar. And then we only have to write ds to zar. And I'm going to give you some more information on zar in the next slides. But this is actually enough to save data into the cloud if the SwiftSpec plugin is installed into FSPEC, and we have the token and the storage URL environment variables in our environment. And we can also remove all the keys from the cloud mapper again by just using the Python dictionary functions. Again, here we use pop, and then we delete the files from the cloud. And this is a cleanup actually. And then last but not least, FSPEC also supports URL chains, and this becomes interesting if we want to use FSPEC as well for access for archives, for example. In this case here, we create a zip container out of all the netcdf files we had looked on. And then we can access one specific file out of the zip container by using the zip protocol. And the double dot here is a separator for different protocols and access protocols. And this is how we chain the URL. We access this specific file from the zip container, and the zip container itself is on the file system in dep.zip. And then we access one file from one zip container. And there are many implementations for backends in the FSPEC, and we can have a look here. I find interesting, for example, there is a Google, what is it called? Drive. Actually, there's a Google Drive backend somewhere, but maybe it's not listed here. But we have also tar backend. We have all kinds of backends, and FTP, for example. And we are also working on a backend for our archive, so that we have then an SLK //URL, which is interpreted by FSPEC. So coming back to the slides, how can we host useful climate data in the cloud? So after we now get a bit of an impression of what cloud storage actually is, I think I have not highlighted it so much, but moves are not actually possible in cloud storages. A move in a cloud storage means actually remove the data or copy the data and then remove the original one. And this is expensive. And that means we have to be sure that the data that we put into the cloud is actually fixed in location. And that means we need a robust path template, in Anführungszeichen. So we need a specific container and a name for the object, and that needs to be fixed like forever. And then we need to allow zar to read the cloud data. Zar is, as far as I know, the one or the best choice, let's say, to access climate data in the cloud via HTTP, or maybe also the only one. library that is that can be used to read climate data via HTTP. And this can be happening either by creating ZAR data that we move to the or that we create in the cloud, or we map other formats to ZAR. And I'm going to show you how this is accomplished in the next slides. And we have to consider that Swift only allows object sizes smaller than 5 GB. And some ZAR compressors also allow only chunk sizes of smaller than 2 GB. And if we stick to the formats that we have maybe already on disk, netcdf or grip, these files correspond directly to objects in the cloud. So if our netcdf files are larger than 5 GB, it doesn't make sense to host them as they are in the cloud. Probably it's even more sure to only host netcdf data which is smaller than 2 GB in the cloud to, if it's compressed. So what is ZAR actually? I haven't give you some background information on this yet. ZAR enables HTTP access also for parallel reads and writes. So if you access data with ZAR on the cloud, then you submit tons of GET requests at once. Yeah, that can be really fast if you have a performant cloud. In Google and Amazon, they reach volume speeds from up to gigabytes per second, many gigabytes actually. It allows chunk-based access to the lowest granularity of data. Chunks are also stored within a netcdf file. So a netcdf file of size of 5 GB might use chunks with really smaller chunks inside the arrays. But you have no access to it from the outside without making some efforts. And it saves metadata next to the binary data. So in netcdf, if you do an ncdump -h, you get the header of the file. And this kind of metadata, plus a bit more metadata, is actually saved next to the binary data in ZAR. And this allows software like EERIE to quickly create virtual dataset representations without opening and loading netcdf files. And if you go further and consolidate metadata across storage, this virtual representation of a dataset can be really huge. And this is actually what ICANN has accomplished with the new next-gen simulations, where they have only 3 datasets for different frequencies. And maybe heel picks is also included, so different zoom levels. But then everything is saved in one. And this is also the idea of the data cube. Save everything in one big data set. And this can be accomplished with ZAR. But ZAR is not only a format, cloud optimized format, but it can be also used. So it's a library. It can also be used to read other formats like netcdf and grip. And it's also, in the meantime, it has become a backend for netcdf. So an NC-ZAR is an implementation within netcdf. So some parts or some URLs for ZAR data can be read by netcdf as well. Unfortunately, not Swift. As far as I know. How is this accomplished? Or maybe we have a look on the ZAR test file first. So we have transferred some FESOM test data, FESOM ng5, into the Swift cloud and shared this. And this is the Swift browser URL. So as I told you, we can share specific containers. And this container here is shared with the world. It's public. And underneath we have this ng5, which is a virtual directory. Only the Swift browser interprets the URL such that it looks like a directory. And within this, you can see a lot of variable names like solar time and such things. And then we have 3 different JSON files. Actually, these are JSON files here: metadata, attributes, group. And all this is part of ZAR. It's the semantic of ZAR. So ng5 is a ZAR file, ZAR container, and that just means that underneath ng5 there has to be Z attributes files, Z group files, Z metadata files. That's a semantic that ZAR provides, so that ZAR is able to understand what's happening inside. And underneath these variables, we have a lot of binary data with numbers. And you can see they have a size of 50 megabytes. And these numbers correspond to chunk indices along the dimension. So the 1 here in the beginning means the first chunk across the first dimension. Second, so after the dot, the second number here corresponds to also 0, or yeah, let's say the 0 is the first chunk. So the first chunk of the second dimension and the first chunk of the third dimension. So, and how much dimension indices are actually in the chunk is then specified in these metadata here, for example, in SERI. If we access it, we can see here, okay, in one chunk, we actually, is this the one? Oh, is it shown? No, it's not shown. Okay, then we leave that. Yeah, you can download it and have a look on that yourself. But in this specific metadata here, it's set how much indices of time, lat, and long, for example, if this would be the dimension, are actually in one chunk. So this is not only one step in each dimension, but it's multiple steps in each dimension. Yeah, and yeah, I think that's it. So if you have this Swift browser URL, you have to only change the start point here of the URL Swift browser DKRZ/public to Swift DKRZ/Fabian, so that the Swift API is actually called, and then you can use this URL and open it with EERIE in your notebook. And this should work from everywhere because it's it's cloud storage, and even it can now even be read with HTTP. So a completely free and public data set can be read with HTTP protocol, not with the Swift protocol anymore. And that means you do not even have to use the Swift spec anymore. This also works without Swift spec, but only if the data is public. Okay, we have seen now that it makes sense if we create new data and we want to save it in the cloud, then we write ZAR, because ZAR is the way to go to save climate data in the cloud. But what about non-ZAR formatted existing climate data? We have actually two options here. We can convert it into the cloud native format ZAR, or we can create reference files to map ZAR, the ZAR format, on netcdf or grep or whatever, and move all the existing data in netcdf and grep to the cloud. And then there's a third way to offer kind of cloud data, the cloudified data, which we are doing here in EERIE. And the question is this first step actually worth the effort? So does it make sense to convert data into ZAR? And we have learned a bit about this step. There are some advantages, there are some considerations you have to do. So of course, if you convert it, you have the best chunking configuration, and you can configure it such that it matches perfectly the access patterns. And that means, I would have to go into detail, but I try. So if users are actually only interested in time series of the entire field, which is assumed in most of climate data applications, but it's not really set. But if you know that, then it doesn't make sense to chunk the special dimension, NZs or lat and long. You can put into the entire lat and long grid into one chunk and only use the time as a one time step in one chunk, meaning that the user then can access fine granular specific time steps in the time series. However, if a user is interested in a specific region, and then you would have to use specific chunk sizes along the special dimensions. So small chunk sizes along longitude and latitudes. So saving the entire grid in multiple chunks and not in one chunk anymore, because otherwise, if a user wants to have only data for Germany of a global grid, the user has to load the entire global grid first. So you can adapt this by, or in this conversion step, no matter what the chunks were before. And then you have the best chunking configuration for the object storage. You can also create the highest aggregation possible, meaning that you can consolidate the metadata for your data. You do not have to provide access to specific netcdf files anymore. You can create a really big virtual data set by consolidating metadata. And the idea here is that subsetting is always easier than merging. So we also aim to provide the highest aggregation possible in EERIE. So you should always have access to the entire time series of the output. And even if it's possible, we could also merge more variables together and create a really big data cube by using ZAR. Yeah, and then we have seen modularity is a big advantage of ZAR. So while in netcdf we have to compile the library and with the compressions that we want to use, in ZAR it's actually modular. So the compression in ZAR is actually done by another library, the numcodecs library. And this is kind of similar to the URL chaining approach. So also the storage in ZAR is made by fspec. And this allows, to be quicker, adaptable to, so modularity is always an advantage in my consideration. However, there are some other things that might raise problems here. So a conversion can mean that we duplicate data. So if we cannot leave the netcdf data and live without the netcdf data or grid data, then we might have the same data set twice, just one time in the cloud. This is probably not what we want to have if we want to save storage, right? Conversion to ZAR format can be tricky. This is because the DAS configuration is not easy and this rechunking costs compute resources. I and Marco and based on some others work, we developed the thesis tool here, which I linked, which might help to convert the data into DAS, into ZAR. It helps, for example, if you have a really large data that you can write by regions to the cloud, meaning that if the HTTP is somehow interrupted and the write process is interrupted, you can just continue where you were and some things. So, but it's 2 years old and things evolving very fast, so maybe you can live without thesis. You can have a look. It's also test some features. And then as a data manager, we have the problem that the completeness of a ZAR data set is hard to verify. The idea of ZAR is actually that the metadata already specifies how much data is inside the data set. It specifies how many chunks are to be expected and so on. And if there are actually no bytes saved for a specific chunk that should be there, then XL translates that to a field of nones. But does it mean that there should be actually data? We don't know. We cannot know this. And this is hard for us as data managers. We need an idea of how we can work with that. Which is also what we also need to consider is if we want to use the ZAR data afterwards for something else, for example, transfer it into into the archive, these small chunk sizes here, these are actually, yeah, if we move that to a local file system, these are files, the 0.0. something. And these are small files. And for example, in the archive, each file counts 1 gigabyte. So if you have 10 megabyte chunk size and we transfer it to the archive, then that fills the archive too much. Also, if we go for even smaller chunk sizes, which can happen when we have high compression ratios, that can even be hard for Lustre because we can have millions of chunks in one directory, which takes a while even for a high performance file system. And then we have a second option here. If we do not want to convert the data into cloud, we can create reference files to map the ZAR format on netcdf or grep, and then move the original data to cloud. And here the idea is to make use of this separate metadata of ZAR. So we use ZAR to read netcdf or grep, and we do that by creating reference files, and reference files use this idea of a file system on a file or on an object. And this again means that a chunk is mapped to a set of to a set consisting of a file, a start byte where to start reading the chunk from the file, and an end byte. For example, in this case, we have a 0 chunk here for variable x, and on the right-hand side here of this, let's call it a dictionary or a mapping. We do not have anymore the bytes, but we have a list which indicates a file system on a file. So we have this file name here, and then we have a start byte and an end byte. And then with the use of fspec, we would read in from that file only the bytes from the start byte to the end byte. And this corresponds to one chunk. And we have tools to map these chunks on the netcdf data, so that we then have JSON files which we can use or which we can pass to ZAR, so that we can read with ZAR the netcdf files. For netcdf files, we have the CareChunk tool, and for grep, we have grepscan. And what they do, they look into the netcdf file and find out the chunks inside the netcdf file, or find out the chunks in the grep file, and then just write it out. They write all these chunks into this kind of format here, and then we can open this. Advantage is we do not have any data conversion, and if we can live with only one copy of it, then we do not have a data duplication. However, we do not have cloud optimization. Does the chunk size match the access pattern? We don't know. We can check how big this chunk size is, but maybe it does not be the best configuration. And one benefit is that the reference file system, in contrast to pure ZAR, moves the chunk indication. So where is the chunk actually from the backend to the user side, and it relieves the backend location. So what does that mean? So while we only have one file specified here, from where we read in bytes, we would have a lot of byte storages for the pure ZAR format, like where we would save for each location a specific ZAR chunk. So we have like millions of ZAR chunks in a pure ZAR file. And for each of this, the file system actually solves where to start reading bytes. While in this case, the file system, the backend, only has to look for this file.nc, and the rest is done by the software and the user side. This can be an advantage for this CareChunk and grep approach. So all in all, a recommendation for bringing existing non-data to the cloud, we have to check maybe 3 things. So this would be my personal recommendation. If the chunk sizes are okay inside the netcdf or GRIP data and the match access patterns and storage requirements. Yeah, so if the netcdf file fits into the cloud and the chunks inside are okay, and the compression that is used inside netcdf is also compatible with the reference file system. So this is something we have to consider. netcdf can use compressions that cannot be translated to ZAR compression, num codecs compressions. If this is also, if you can answer this with yes, and you can also live without a disk storage version of the data, and you can live with 1 copy of the data, even on a not backupped cloud, then yes, we can go for option 2. We do not have to convert the data, and this might be less fault tolerant. So on a conversion to ZAR, we have seen, for example, we cannot say if the ZAR is complete. We do not know. So we would have to do a complete twice quality control, right? So is the ZAR output okay? Not, yeah, it's a kind of an effort to convert data to ZAR, but yeah, we have seen that it can be worth it. So data workflow at DKRZ for EERIE. For raw netcdf output, this is important. So we, of course, plan to standardize and to publish in ESGF data. Right now, we want to host and make the EERIE data accessible as soon as possible, and this is why we have a specific data workflow for the raw output. We can recognize that using ZAR to open data is even helpful on file system, not on cloud storage. Independent of the backend storage, it makes sense. If we can do it, we should map netcdf to ZAR and create those reference files, because we then can use only 1 metadata file to open thousands of netcdf files. And this is what we do in EERIE actually with EERIE and the intake catalogs. And we just achieved by switching to Parquet reference files, which is kind of a compressed version of this reference JSON, that we only save a file of the order of a megabyte for 100 terabytes of data. And this also means that if you open this, your memory inside the notebook is also less than a gigabyte, only like a few megabytes for opening the data. This is really helpful. Yeah, so the picture here means that on the left-hand side is the starting point. The Earth system model here produces output on the file system. And then a cron job creates those reference file snapshots of chunked and aggregated EERIE data sets, so that we have kind of a virtual object storage. Virtual object storage, I mean that, so this reference file system actually looks like, yeah, let's think about this mapper again. So this is nothing else than this key value JSON file that we have. It's a virtual object storage. And then we're going further we host these data, which is actually on work, with data servers to the world. And at Wachsmann, it's possible to host each and every project space, as far as I understood, if yeah, it's requested to the system admins and if you use a specific directory. Right now you have to apply for access at Wachsmann, and most of the climate data for EERIE is saved in the specific directory that it can be yeah, made accessible via HTTP to the world. At DKRZ, we have an XPublish server to host the data. And this is here the second step in the PNG. And XPublish serves the data sets dynamically. So the idea is that this reference file creator is actually run in a cron job, so that we have always a live view on the output. This is not yet implemented, but it's not far away from implementation, and we hope to have that for the next experiments for ICANN and even the other models, IFS FESUM 2 maybe. And then we use these URLs, not only xpublish, but also the work URLs, and collect them in an intake catalog, and users can use intake to open it and do not have to care about the backends and whatever reference and such things is actually used. So why xpublish? xpublish allows us to add some server-side processing for data volume reductions like compressions, aggregations, or diagnostics. And we learned in the hackathon from some guys that they actually, so what brings fair data if the fair data has a volume of so many terabytes that no one's able to download it. So we have to think about adding more volume reduction methods to have better services, I think. And this is where xpublish can help. So we can lossy compress data, and then the time that the server needs to compress is not so much as if you would wait for the entire download of the not compressed data, if you have the space for it. Yeah, so what has happened? Updates on the data access user supports. There are some updates on the EERIE Cloud server. You can have a look, for example, easy group by operations. This is work in progress. The idea is to put some, for example, temporal group by operations with EXARRAY here into the API that you can call it via the HTTP URL here. In this case, we group by the TAS from the daily minimum output here. For each month, it's coming from a daily output, and then we get the mean over each month. So this is just a monthly mean with EXARRAY. And this will be provided as on demand. So if the user requested it, then it will be calculated by the server, not before and not afterwards. We also have implemented a interactive plot generator, but this is right now only a backend. So if you have time and you are interested, you can develop a front end. I didn't have succeeded to do that. How the API calls works can be seen here under this URL, the HTTPS EERIE Cloud DKRZ docs. And maybe I show you this one. Let it work. Okay. We also updated notebooks to access database intake. So how to work with the disk data on DKRZ, we have a full guideline on intake, and the intake catalog now supports also some plots in the notebooks, and we have support for intake ESM. In the hackathon, we only worked with the pure intake and intake EXARRAY. We now have also support for intake ESM, which was used by Wachsmann, so you can work with both. Intake ESM is better if you do not really know what's inside the catalog, because it allows you to already see what can you use to search. So what are the attributes in the catalogs, like source ID, experiments, and what are the unique values inside the catalog for these specific search keywords like experiments and so on. And then we also show how you can make access of the DKRZ xpublish server, how you can access the data from there, from everywhere. And so now I want to conclude here with a call for feedback. We really would like to know what was the obstacles that you have during the hackathon regarding data access. Can we make things better for the next hackathon? We also would like to share your specific hackathon results. Maybe it's possible to host custom diagnostics on the xpublish server or put them in the intake catalog. If you're interested in that, come to us. We can help you with that. This is something to discuss. What variables are actually suitable for the cloud? And this is something we can openly discuss, I think, because there's no scientific statement what is more suitable than others. And this was it. Thank you very much.
Thanks a lot, Fabi. I just put clapping hands. So while people are thinking about the question, maybe I will start with so currently the only way how you can work with the data that I expose through this ZAR located on DKRZ is you can select some portion of the data and actually download it, right? So, well, I mean, except for the things in development that you showed right now, that you can also do some visualization with it. But I mean, the default way of working with the data is basically you open the data, like for the outside version, you open the data, you see, okay, I'm interested in these 5 points across all of the time span. I would like to download them. Is it the main thing? So, I mean, there is no processing associated by default with this data. You cannot really do some, I don't know, time series analysis immediately on the data that you have in the ZAR, in the cloud.
So you are referring to the EERIE Cloud server, right? That's what you.
Yeah. So this thing that with the NG5 that you showed.
Ah, the NG5.
Yeah. Yeah.
No, I'm a bit confused. So not the EERIE control, but these ZAR data in the cloud. Okay.
Yeah, ZAR data in the cloud.
No, this is something where we would have to collect the URL in an intake catalog, and then you open it, and you would then have no server-side processing right now. However, I could, of course, include cloud URLs into the EERIE cloud server, and then we could use the EERIE cloud server to do computations.
Well, I mean, just from the point of view, of the person who is coming from the outside. So somebody just want to work with EERIE data, and that would be just similarly to ESGF, just exposition. You just expose this data, except for that you don't have to download all the netcdf files that you're interested in, but you just can download the part of it.
Yeah, the difference is in ESGF you have most likely larger entities, files that you have to download, although you're only interested in smaller chunks. And if you access the data via cloud, for example, also the NG5, you have seen one chunk size is like 50 megabytes. Yeah, maybe this is already enough for your analysis because you're interested in one time step and the entire thing. So this means that you reduce download volume at this point. Computational resources are not within that cloud storage by default, no.
And just another thing, like if I would like to create by myself something that's similar to this NG5 archive that you showed, is it something that I can do myself, or it's something that I have to ask you to do?
So in my experience, for daily data, even it was 3D, this 2ZAR, which I showed in one of the notebooks in the FS Spec tutorial, actually worked. It takes many memory gigabytes, but it should be within a Jupyter notebook on Levante, you should be able to transfer the data into ZAR format in the cloud with the 2ZAR,
and then I can just open it as like, or give it to somebody, just make it public, give it to somebody, and then they can work with it as with ZAR.
Yeah.
Okay, cool. Yeah.
Right.
So are there other questions to Fabi? Well, yeah.
Thanks, Fabi. A lot of work that you've put in. I'm still trying to figure out. So the cloud that you have it for, it's to relieve some of the disk space that is on disk, or is it to give access of the data to the larger audience that's not within EERIE? Or I'm still struggling a little bit about how I'm doing the analyses, right? Should I be accessing the data then from the cloud, or am I accessing data from disk? Should I be actually creating data on the cloud? I'm trying to figure out what is it that.
So my intention was that you should lose the fear of using the cloud just as storage as everything else. So you can use it as if it was the disk storage for your analysis. I mean, I was open to you. I told you that there's no backup for the cloud data. For some cases we have to be careful, but for some analysis results, for example, especially if you want to share analysis results, cloud storage is perfect. Also, of course, you can exit it from everywhere. You can exit it from Jasmine without authentication. You have to make the data public then.
Right.
Yeah. So actually, everything you said was kind of what I would also support.
Okay.
But I think like by default, I think for you as a person who have access to DKRZ, like if you want to work with the data, I think at least from my point of view, I would still use the data on the disk directly, and cloud is more like if you really want to share the data. But on the other hand, my experience from converting the data to ZAR and compressing them shows that first of all, they become smaller, which is a big problem for us. And second of all, it's faster to work.
Smaller.
Well, I mean, if you compress, yeah. So if you
but why is it a problem?
No, it's not a problem. The big problem for us is that we have a lot of data and that we actually have to compress them. It would be nice to compress them, right? And that's one thing. They become smaller, which is good. And another thing is that working with them become faster because the current algorithms for compression are so fast that it's faster to load smaller amount of data from the disk and then uncompress them in the memory than to load the whole uncompressed data. You see what I mean?
Okay. Yeah.
So you're loading the data, smaller amount of data, you expand them, then you spend some computational resources to kind of unpack them, but it's actually like
crazy.
50% faster than just
unbelievable.
Yeah.
So pardon my ignorance, how different is it to syntax-wise and things like that when we're using intake and then it points to .NetCDF files or something like that versus if we're supposed to use the ZAR? Like, does the user have to know if we are accessing data that is ZAR format or if it's just whatever we search through the intake catalog? Like, is there basically prerequisite?
Well, ideally, it shouldn't really matter. Ideally, it should look the same for the user. But I mean, we should.
Right.
It's like for people who create the data and who process the data, it's important how to organize them. But people just open the data set. Who cares? I mean, ZAR.
So the dream of intake is, of course, not only that it does not matter what the format is, it should also does not matter what the backend storage is. And just open the catalog, load it. Is it in archive? It doesn't matter. Is it in cloud? Doesn't matter. Of course, we will see that it matters because loading data from an archive takes longer. But at least for cloud and disk, we can try to make them more on one level, you know. And also, I just wanted to make you able to work with the cloud. We have like 100 terabyte in it. We can use it. We can put data into it. Yeah, release some data on disk.
So I guess that's why I was asking for the cloud. I mean, 100 terabytes, which is quite a bit actually. I was thinking more of if it's like, for example, when we're interpolating data or something, we're sharing that, right, quite a bit because we want to do intermodal comparisons. That seems like a good platform. But you showed the Swift browser too. I mean, that's also a place where we could share quite a number of figures, right?
Yes.
Okay. Okay. I guess, yeah, I still have hesitancy to use the cloud because I don't know what I'm doing on it. But okay.
Yeah, just give it a try. I hope now if the Swift spec is now in the Python 3 unstable kernel, so you don't have to install something, you just have to bring this environment variables into your environment and then, yeah, use fspec and use ls and copy and, or maybe not copy, but pipe and all this stuff. And
But you said download and copy. That means we're actually downloading it somewhere, or is it? I thought the whole point was that if there's data already on Levante, we don't need to download anything.
download. Now I'm confused. So, well, download, did I say download? What I didn't want to say download.
So it's just data access then?
Yeah,
Sorry,
you can access, like, I mean, you can, it's just another place to store the data with some peculiarities of how to put data there and how to extract data there. But in general, yeah, especially for you who has access not only for the cloud storage itself, but also for the compute, it shouldn't be really
Shouldn't be a
a lot.
problem.
Yeah.
Okay.
So like when you want to process the data, it's a problem for the people outside of DKRZ because they would have to first download the data and then compute the data. But for you, I mean, the data will be like when you process them, they will be processed inside of the DKRZ, so it doesn't really affect that much.
That was the question. Yeah. That being said, of course, the protocol that is used even inside DKRZ is HTTP. So it kind of is a download. It's a download on very small distances. Maybe that's the reason why it's faster. Then it's kind of a download, but it's a load into memory, not a download. Yeah. You would have to do the same if you work with disk. Just use a different protocol.
Yeah, but something that we can test as well. How fast it's actually to do the processing on the cloud through this. But I mean, people put this the data from CMAP6 models, for example, on the cloud, and they processing them there as well, and that's pretty fast.
So I think also one really good advantage is that when Levante has maintenance, you can still work with your local laptop on data that is in the cloud. And sometimes it really is a nice thing. So because you can still look into things. Do not have to stop work.
Yes, but in that case, like, so you're accessing the data and then you're just working on the cloud itself and have all the programs there, not on the laptop? What do you mean by like you can access it by the laptop, but would you have to download the data then onto your laptop to be doing stuff?
Yes, but the question is, what are you doing with it? I mean, sometimes you're looking into plots that won't take so much of downloading and things. Of course, if you want to do a big analysis, that would mean lots of download, yeah. But still, you have access to it.
Okay.
I think by the end of EERIE DM, you will be doing everything in the cloud. So just need something to get used to it.
Okay.
I think I have to close it if there is no like very urgent questions because we're already 15 minutes over, and I also have to run and pick up my kid. So
okay.
So anything like super urgent that the last question to Fabi? So the materials will be online, right? So all the links will be in the presentation that will be attached on the EERIE website. If you have some ideas for the next Science Hour, you're very welcome to contact people. Either me or Dian probably will also go, but we will redirect you probably to people. And yeah, so the next one probably will be in January sometime. All right. So
Perfect,
thank you very much. Happy, yeah, all
Merry
the
Christmas, Happy New
upcoming
Year, everything.
Thanks, sir.
year,
Happy holidays.
Christmas, and whatever you're celebrating. Yeah.
Thanks,
Okay.
bye.
Holiday season.
Thanks a lot. Bye bye.
Bye.